Hey guys, what's going on? This is part 2 of neural networks from scratch using Python. So in this tutorial, we're actually going to be doing the coding and building our neural network. So in this video, I'm going to be working with the Kaggle notebook. However, if you want, you can work with something like Google Colab. It's totally fine, it's up to you. So to work with the Kaggle notebook, just head over to kaggle.com, create a new account, and now we're going to be searching for the dataset which we'll be using today, which is the MNIST digit recognizer dataset. Let's press search, and then we're going to be using this one. So this dataset stores images of handwritten digits. So basically, we're going to be building a neural network which will be able to identify given images of handwritten digits. So if we give our neural network an image of 0, it should be able to hopefully tell us that it is indeed an image of 0. So to start working with this, just click on New Notebook. I already have a new notebook here. And the first thing we need to do is we need to import all of the required libraries. So I'm going to import pandas as PD, and we also need to import NumPy as NP, and we also need the matplotlib library. So from matplotlib, import pyplot as PLT. So we need the matplotlib library for visualizations, and we need the NumPy library for working with multi-dimensional arrays, and we need pandas library to read in our CS3 file. So let me just press run, and then click on code to make a new cell. And now we can go ahead and use the read CSV function from the pandas library. I need to pass in a file path. So we can just click here to copy the file path, and then type / then train.csv, because this is the name of the file, as you can see here. All right, now we can just store this in a variable. I'm going to call it data, and then we can just use the head function. This is going to give us back the first 5 rows from the data set. Just wait for it to load. All right. Here we can see that each individual row represents an image. So this entire row is an image. This entire row is an image. And this each column represents an individual pixel value. So we have 783 pixels. And the first column represents a label. So this label right here tells us what this image is. So this image, this entire row corresponds to an image of 1, and this entire row corresponds to an image of 0, and so on. So now what we can do is just click on code to make a new cell, and now we can just convert this array into a NumPy array. So we do it like this. So np.array of data. So basically we're going to take all of this data, convert it to the NumPy array, because it's much more efficient to perform operations on a NumPy array than a standard array. All right, so now after this, we can split our data. We have our data in the form of a NumPy array. Now we can split it into 2 different parts. We can have a testing set and a training set. So if you recall from the previous video, we need data to test, to train our model. We're going to first train our model, then we need data to test our model to see if it works as we expect it to. So first I'm going to set aside data for training. We're just going to do it like this. So data, this is going to give us back the first 1,000 samples. And then we can do a .t to do a transpose. So basically what transpose does is that it takes the rows and converts into a column. So it's like, you can think of it like flipping the array by 90 degrees. So let me just show you what that looks like. So let's say I have an array like this, which is let's say 4 by 3, and it has these rows 1, 2, and 3, and 4. If I do a transpose, I'm flipping it by 90 degrees. So I'm gonna get something like this. So now all of the rows are going to become columns. I'm going to get an array of 3 by 4. So 3 rows and 4 columns. So this entire column is now going to become a row. So I'm going to get 1, 2, 3, and 4. So this is what a transpose does, basically. And then I need to set aside, once I have all of my images which I'm going to use for testing my neural network, I need to set aside the labels and the inputs. So I'm going to call the labels y-test. So basically, I'm going to extract all of these labels which tell me what the image represents. So I can do that by getting the 0th element from the test. Now the reason why this is because, if you recall, when we do a in our original array or original data, the first column represented the labels. So after we did a transpose, the first row became all of the labels. And if we extract the 0th element from the test set, this is going to give us back all of the labels. Now we can extract the X test, which is going to be all of the all of the pixel values. That is going to be test of 1 up till 783. And why is that? Because originally all of these columns represented the number of pixels, or how many inputs that we had, number of pixels. And after we did transpose, now the columns will become the rows. So now, after doing a transpose, this represents the number of rows represents the number of pixel values that we have, which is 784. So we know that the zeroth row is going to be the labels. Everything after that is going to be the image data. So from the first row, or the second row, which has an index of 1, all the way up till the last row, that is going to be our input data, which is X test. Now we can set aside, we need to do one more thing. We need to normalize the data, meaning we need to bring all of the values in the input in a range of 0 to 1. So we can do that by like this. So X test is equal to X test over 255. This is going to basically divide each element in the array by 255, which is going to bring it in the range of 0 to 1. So we can now, after we're done with the testing set, we can just copy this, and now we can also do the same thing for the training set. I'm just going to call it train, and now instead of the first 1,000 samples, we can just get everything else that's remaining. So starting from 1,000th position, everything else that's remaining, meaning all the images that are remaining after the 1,000th image, and then we're going to transpose that again, meaning do a shift of 90 degrees, so all of the rows become columns and columns become rows. And then we're going to extract the 0th element, which is going to be all of the labels. So that's going to be white, I'm going to call it white train. So the labels for the training set, and we also need the white X train, which is going to be all of the input data. Again, this is going to come from the training set, and we also need to divide the inputs by 255. I'm going to call it X train, and it seems we have a small typo here. It's X underscore test. Alright, I'm just going to run this. Alright, so before we move further, it's important to discuss what the structure of our neural network is going to be like. So in the input layer, we're going to have 784 different neurons because we have 784 pixel values. The hidden layer is going to have 10 different neurons, and the output layer is going to have 10 different neurons as well, because we have 10 different possible outputs. So a given image of a handwritten digit can be any number in the range 0 to 9. Now we can start coding our first module, which is going to be initialize parameters, and this is we're going to be setting the values for all of our parameters. So first we're going to have w1, and remember I said that we're going to have random values for these at first, so we're going to use the numpy library. We're going to use the function random.randn. So this is going to create an array of which is going to be filled with random values, and we need to specify what the dimensions of this array are going to be. So the dimensions for this are going to be 10. It's going to have 10 rows, and it's going to have 784 columns. Now the reason why I picked these numbers is going to make more sense when I explain the forward pass in a few minutes. Right. So after w1, we're going to have b1, which is going to be the bias for the first layer, and it's going to be np.zeros. So it's going to create an array and it's going to fill it with zeros. Again, we need to for this we need the double brackets. We need two parentheses, and we need to again specify the shape, which is going to be 10 and 1. So 10 rows and 1 column, and then we need w2, the weights for the second layer. Again, we need to do np.random.randn. It's going to create an array and fill it with random values, and the shape or the dimensions for this is going to be 10 and 10. So 10 rows and 10 columns, and the bias in the second layer is going to be np.zeros. Again, we need the double brackets, and we need to specify the shape, which is going to be 10 and 1. Then finally we can return all of these. So return w1, b1, w2, and b2. Alright, so now we're going to do the forward pass. So if you remember from the previous video, recall that in forward pass we process each layer one by one sequentially, and each neuron has two different parts. It has a linear function and it has the activation function part, and we need to compute that for every single neuron in each of the layers. So I'm going to define a function here. I'm going to call it forward pass, and it's going to take in a few inputs. It's going to take in x, which is going to be the image data, our original input, and we also need the parameters. We need w1, b1, w2, and we need b2. So first I'm going to define a variable. I'm going to call it z1. So this is going to store the output of the linear function for all the neurons in the first hidden layer. So instead of calculating the output of the linear function for each neuron individually, we're going to do all of it in just one step. So let me show you what that looks like. I'm going to do np.w1 and x. I'm going to add a bias term to it. Alright, so don't worry if this step did not make sense. I'm going to explain this right now in much more detail. So here we have a simple diagram of a neural network, and then we have all of these arrays which we're going to be working with right now for the first layer. So we have w1, which are the weights for the first layer, and we have the x which is the input. We have b1, which are the bias terms which are associated with each one of the neurons. So we're going to have 10 of these because we have 10 neurons in our hidden layer. Then we have z1, which is basically the output, the output array of the linear function. Alright, so how does this work? We did np dot w1 and x. So what does that mean? So basically np dot means we're going to take all for each of the neurons. So starting with the first neuron, we're going to take all of these inputs, x1, x2, and x3, all the way up to 784, because we have 784 different inputs. We're going to take all of these 784 inputs and multiply them with the corresponding weights. So we have all of these lines which are connecting to the first neuron. In this simple diagram, we have only 3 of them. We have W1, W2, and W3, but we're going to have more. We're going to have 784 neurons. So there's going to be 784 different weights or connections which will be connected to the first neuron. So we're going to take all of these inputs, and multiply them with the corresponding weights. then add all of them together. So it's going to be something like this. We're going to take this entire row, which corresponds to these weights for all of these connections for the first node, and we're going to multiply them with this entire column. So this column represents our inputs, all of the inputs. So you can see the number of rows for this array is the number of inputs, which is 784. So we have 784 different input features, and each column represents a single training example. So this is the first training example. We're going to take W1 times X1, W2 times X2. We're going to multiply all of these weights times the corresponding inputs, then add all of them up together, and then finally we also added a bias term to it. So because we're dealing with the first node, we're going to add up the first bias value. It's going to have some value here. We're going to add it to the result. And then we're going to get some output. I'm going to label it as Z1.1. So just a quick recap, what did we do here? We took all of the inputs. Which are these right here. Then multiplied them with the corresponding weights, which we got from here. Then we added all of them together. So W1 times X1 plus W2 times X2 plus, we keep adding them all the way up to the last value. And then finally, we add the bias term to it, which is going to be some random value at first. And then we're going to get some output. We're going to store it here in this array Z1. So that'll be Z1.1. And then we have more training samples. So I'm going to just label it as X1.1, X1.2, and so on. So all this is going to be the data for the second training sample. So again, we do the same thing. We're going to take all of these weights, then we're going to multiply that with the input data for the second sample. So it's going to be W1 times X1.1, W2 times X1.2. Then we're going to keep on doing that till the final value, and we're going to add all of them up, and then we're going to add the bias term again, and then we're going to get some output that will be Z1.2. So this is for the first node. Again, we're dealing with the first node. This was for the first sample, this is for the second sample, and we're going to keep on repeating this for all of these samples. So again, we're going to have input values here. For our third sample, that's going to be X1.3. I'm just going to say that this is X3.1, X3.1, X3.2, X3.2, excuse my handwriting. So we're going to take all of these weights, multiply them with the corresponding input values, add them all together, then add a bias term to it. That will be the output of the linear function in our first node for the third sample. So that will be Z1.3. Then we can keep repeating this for all of our samples. Then once we're done with that, this is everything for the first node. We're just done with the first node. We need to do the same thing for the second node and all of the other nodes. So this node right here, you can see we still have the same inputs. But what's different now is we have different sets of weights. We have different lines which are connecting to this node. So we have different weights or different connections. So that corresponds to the second row over here. This row over here, the second row. I'm going to just call it W1.1, W1.2, and so on. So we're going to take all of these weights. Again, we're going to multiply them by the inputs, corresponding inputs. So W1.1 times X1, W1.2 times X2, keep on multiplying the weights with the corresponding inputs and add them all together. And this time we're going to add the bias. When we add the bias, we're actually going to be adding the value from the second row. And why is that? Because we're dealing with the second node, right? So this is the value for the second node. Then we're going to store the output. I'm just going to call it z2.1. So this is the output of the linear function part for the second node for the first training sample. Again, this is the first training sample, and this is the second sample. So for the second sample, we're going to take the weights. These are the weights. We're going to multiply them with the data, the input data from the second sample. So W1.1 times X1.1, W1.2 times X1.2. We multiply all the way up till the last value. Then we add all of them up together. Then we add a bias term. Then we're going to get some output. That's going to be Z2.2. So second node, second training sample, right? Because we multiply the data for the second training sample. We can keep on repeating this for all of the samples. So the dimensions for the Z1 array, the number of columns is going to be the number of samples. Let me just write that down. Number of samples. How many images do we have? And then this is just for the first two nodes. We're going to have to repeat that for all of the neurons in the hidden layer. So that's 10. We're going to have to do the same thing for all 10 neurons. So we're going to take the inputs, multiply them with the corresponding weights, add them together, then finally add a bias term to it, add the corresponding bias term to it. That's going to be the outputs of the linear function for all the nodes. So that we're going to have 10 rows. We're going to keep on repeating the same thing. Just take the inputs, multiply with the corresponding weights, and then add the corresponding bias term. That's going to give us the output of the linear function for all the neurons in the hidden layer in just one step over here. Alright, so after we have the linear outputs for the first layer, we can move to the second part. We can calculate the output from the activation function. Now, if you recall from the previous video, the activation function that we use in the hidden layer is called the ReLU function. So let's just define that. I'm going to create a new cell. I'm going to create a function. I'm going to call it ReLU. It's going to take in some input, and it's going to just return max of x or 0. So what this does, if we pass in a positive number as input, it's going to give us back the same positive number as output. If we pass in a negative number, it's going to give us back an output of 0. So what this is going to do, basically we're going to apply the ReLU function on this linear output right here. So we're going to pass in Z1. So what this is going to do is going to take, so basically we have this array Z1 which stores the output of the linear function for all of the neurons. So there's going to be 10 different rows. The ReLU function is going to take each value, each element inside of this array, and it's going to apply the ReLU. It's going to apply this function to every single element. So, for example, if let's say Z1 was 10, Z1.1 was 10. After applying the ReLU of max of x or 0, the output is going to be the same number, 10. So it's going to do the same thing. It's going to apply the ReLU function max of x or 0 to every single element in this array Z1. And it's going to give us back a new array with all of the outputs of the activation function. And we're going to call it A1. Alright, so this is the output of the activation function for all of the neurons in the first layer. Then we can go ahead and compute the same thing for the second layer. We can do the same kind of thing. We're going to take all of the inputs, all of the weights, multiply them with the corresponding inputs. But this time, what are the inputs going to be? So for the output layer, we have 10 neurons. We're going to have 10 different neurons. just going to draw some here. All right, so we have 10 neurons, and the input for this layer is going to be the output of this layer. So what is the output of this layer right here, the first hidden layer? It was A1. A1 is the output that we got from this first layer, as we can see here. A1 is the output of the first layer. So this is now going to become the input to the next layer, to the output layer. So what we can do here is we can just replace x with A1, because A1 is now our input for the second layer. And now we need to add the bias term, which is B2 right here. And then to calculate the activation function for the output layer, if you recall from the previous video, what we did for the output layer was we applied a sigmoid function. So let's just define that. A sigmoid function. Defs, it's going to take some input, and it's going to return back 1 over 1 plus np.exp, which is the exponent minus x. So what's this going to do? It's going to take in a input, which is this right here, basically the output of the linear function from the second layer, which is this part right here for all of these neurons, and it's going to apply the sigmoid function to every single value in the output layer, which is this function right here, 1 over 1 plus e to the power minus x. That is the sigmoid function. It's going to apply that to every single, basically we have an array. We're going to have an array, which is Z2, which stores all of the outputs of the linear function from the second layer, from the output layer, which is our second layer, and it's going to apply this function to every single element in this array. And if you recall, what this sigmoid function does is that it brings every single the input in the range 1 to 0 to 1, basically. So it's a function which looks something like this. All right, so that's basically the sigmoid function. So we can apply the sigmoid function to Z2, and basically we're done. So now we can return all of our outputs, Z1, A1, Z2, and A2.